The sound echoed across the firing range at Kokura Arsenal on the morning of October 12th, 1943. Not the sustained thunder that Colonel Iwakuro Hideo had expected, but something worse, a mechanical scream followed by silence. The prototype machine gun, designated Ho 103, had fired 47 rounds before the belt feed jammed, the barrel assembly seized, and 3 months of precision work revealed itself as failure. Iwakuro stood motionless in the observation bunker, his eyes fixed on the smoking weapon mounted on its test stand. Around him, engineers and technicians exchanged glances but said nothing. The silence was broken only by the distant clatter of the arsenal's main production lines, where thousands of workers assembled proven weapons that actually functioned. But not this one. Not the gun that was supposed to give Japan what America already possessed. A heavy machine gun that could fire reliably at altitude, shred enemy aircraft, and sustain combat far longer than any weapon currently in the Imperial arsenal. The Ho 103 was Japan's attempt to copy the Browning M2, the 50-caliber machine gun that armed every American fighter, bomber, and patrol boat in the Pacific. Iwakuro had seen the Browning's devastating effectiveness firsthand during his years as a military attaché in Washington before the war. He had watched demonstrations at Aberdeen Proving Ground, where American gunners fired thousands of rounds without stoppage, the weapon cycling with mechanical perfection that seemed almost supernatural. When war became inevitable and Iwakuro returned to Tokyo, he brought with him detailed notes, photographs, and a conviction that Japan needed this weapon more than any other piece of American technology. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Now, standing in the cold October morning air, watching technicians approach the failed prototype with wrenches and testing equipment, Iwakuro understood what his 3 years of effort had produced. A machine that looked like a Browning, that mimicked its dimensions and mechanisms, but that could not replicate its soul. The Americans had built a weapon from abundance, precision, and industrial systems that Japan could not match. The Japanese had tried to copy it using substitutes, approximations, and desperation. And every time they pulled the trigger, physics delivered its verdict. The path to this moment had begun not with ambition, but with humiliation. In the early months of the Pacific War, Japanese naval aviators and bomber crews faced an opponent they had not anticipated: the American 50-caliber machine gun. It appeared on everything. Wildcats and Dauntlesses carried multiple guns in their wings and flexible mounts. Flying fortresses bristled with them in power turrets that could track targets with mechanical precision. Even patrol boats mounted them for anti-aircraft defense, creating fields of fire that turned low-altitude attacks into suicide missions. Japanese aircraft, by contrast, relied on rifle-caliber weapons and 20mm cannons that represented opposite ends of a problematic spectrum. The Type 89 7.7mm machine gun, license-built from British Vickers designs, lacked stopping power against increasingly armoured American aircraft. Pilots reported emptying entire ammunition loads into enemy bombers, only to watch them continue flying, their self-sealing fuel tanks and redundant systems absorbing damage that would have destroyed any Japanese aircraft. The 20mm Type 99 cannon packed devastating punch, but its slow rate of fire, around 500 rounds per minute, and limited ammunition capacity made it unsuitable for sustained combat. The 50-caliber Browning occupied the perfect middle ground, heavy enough to penetrate armor and destroy critical systems, fast enough to fire 800 rounds per minute, and reliable enough to sustain combat operations that lasted hours rather than minutes. When the Imperial Japanese Navy's Technical Intelligence Section examined their first captured Browning M2, recovered from a downed Wildcat near Rabaul in March 1942, the weapon's sophistication became immediately apparent. The Browning used a short recoil operation, where the barrel and bolt recoiled together for a brief distance before unlocking, allowing the bolt to continue rearward while the barrel returned to battery. This mechanism, perfected by John Browning in the 1920s, distributed forces in ways that reduced wear on components and maintained timing precision across thousands of firing cycles. The feed system used a complex linkage that pulled cartridges from a disintegrating metal belt, positioned them for chambering, and ejected spent casings with mechanical elegance that required no blows, adjustment, or operator intervention. Every dimension of the weapon reflected manufacturing precision that Japanese arsenals struggled to achieve even in peacetime. The barrel, chrome-plated internally to resist erosion from hot gases and copper fouling, maintained accuracy through sustained fire that would have burned out Japanese barrels in minutes. The headspace, the critical distance between the face of the bolt and the base of the cartridge, was set with tolerances measured in thousandths of an inch. Too tight, and the weapon wouldn't chamber rounds reliably. Too loose, and case head separations would destroy the gun. The Browning maintained perfect headspace through temperature extremes and vibration that turned Japanese weapons into scrap metal. But what truly distinguished the Browning was its interchangeability. Every component was machined to specifications so precise that parts from one weapon could be installed in another without hand-fitting or adjustment. American armorers could swap barrels, bolts, or entire receiver groups in minutes, maintaining combat readiness with logistics that resembled automotive repair more than traditional gunsmithing. This was mass production elevated to art, and it required industrial systems that Japan simply did not possess. The decision to copy the Browning rather than develop an indigenous design reflected pragmatic reality within the Imperial military establishment. By mid-1942, Japan's industrial capacity was already strained beyond sustainable limits. Shipyards worked around the clock to replace carrier losses from Midway. Aircraft factories struggled to meet production quotas, while Allied submarines strangled the flow of raw materials from occupied territories. Steel, copper, and chromium, the essential materials for weapons production, were being rationed with increasing severity. Designing a new heavy machine gun from first principles would require years of development, extensive testing, and manufacturing infrastructure that didn't exist. Copying a proven design, especially one for which intelligence had provided detailed technical drawings and captured examples, seemed to offer a shortcut that Japan's desperate strategic situation demanded. The Navy's Bureau of Aeronautics assigned the project to Kokura Arsenal, the facility that had previously produced successful copies of foreign weapons, including the Type 11 light machine gun derived from the French Hotchkiss design. Colonel Iwakuro, recently returned from his posting in the United States, was appointed technical director. His orders were unambiguous. Produce a functional copy of the Browning M2 within 12 months, suitable for installation on naval fighters and bombers, with production capacity of at least 500 units per month. The implied message was equally clear. Failure was not an option that Japan's deteriorating air war situation could afford. The initial assessment team that disassembled the captured Browning spent 3 weeks carefully measuring, photographing, and documenting every component. Their report, submitted in April 1942, ran to over 200 pages of technical drawings and specifications. It also contained a section that Iwakuro read with growing unease, a list of manufacturing challenges that would complicate or possibly prevent successful replication. The barrel required internal chrome plating using electrochemical processes that Japanese arsenals had not mastered for weapons production. The receiver demanded precision machining on milling equipment with capabilities that existed in only a handful of facilities, all already operating at maximum capacity for other critical weapons programs. The feed mechanism used hardened steel components with surface finishes and heat treatment specifications that pushed the limits of Japanese metallurgical practice. Most troubling, the weapon's design assumed access to ammunition manufactured to American-side specifications, with consistent cartridge dimensions, powder charges, and primer sensitivity. Japanese .50 caliber ammunition, produced in limited quantities for experimental anti-tank rifles, showed significant variation between production lots. Iwakuro understood that these challenges represented not merely technical problems to be solved through engineering cleverness, but fundamental mismatches between American and Japanese industrial systems. The United States produced weapons, assuming abundant materials, specialized machinery, and workers trained in specific tasks. Japan produced weapons, assuming material scarcity, general-purpose machinery, and craftsmen who hand-fitted components to achieve final tolerances. The Browning M2 was a product of its industrial environment, Copying its form without replicating that environment was like trying to transplant an organ without matching blood types. Nevertheless, the order stood. The project received priority classification, which meant access to limited supplies of strategic materials and authority to requisition skilled workers from other programs. Iwakuro assembled a team of 42 engineers and technicians, many of them veterans of previous weapons development programs. They established a secured workshop within Kokura Arsenal, sealed off from the main production floor, where the captured Browning could be studied without risking intelligence leaks that might reveal Japan's intentions to copy American weapons technology. The first decision involved whether to create an exact copy or to redesign components to accommodate Japanese manufacturing capabilities and available materials. Iwakuro initially advocated for exact replication, arguing that any deviation might introduce unforeseen problems that would require expensive testing and development time Japan didn't have. His chief engineer, Nakamura Shoji, disagreed. Nakamura had spent 15 years at Kokura and understood the arsenal's limitations intimately. He argued that several components, particularly those requiring chrome plating and exotic alloys, would need to be redesigned using available Japanese materials and processes. The compromise they reached would ultimately doom the project, though neither man recognized it at the time. They would copy the Browning's external dimensions and basic mechanisms exactly, maintaining interchangeability with American ammunition and allowing the weapon to fit into existing aircraft installations designed around the M2's size. But internal components would be modified as necessary to accommodate Japanese manufacturing reality. The barrel would use conventional steel with nitriding surface treatment instead of chrome plating. The bolt and other high-stress parts would use Japanese alloy steel rather than the specific grades specified in American technical documents. The feed mechanism would be simplified to reduce the number of precision-machined surfaces, requiring extensive hand finishing. Each modification seemed reasonable in isolation. Collectively, they transformed the weapon from a precision instrument into an approximation that inherited the Browning's complexity without capturing its reliability. By August 1942, the first prototype components were emerging from Kokura's machine shops. The receiver, machined from a forged steel billet, looked identical to its American counterpart from the outside. But the tolerances, measured and documented by quality inspectors, showed variations that would have failed American military acceptance standards. The bolt face, which needed to be perfectly perpendicular to the bore axis, showed angular deviation of nearly 1/10 of a degree. The locking surfaces that held the bolt closed during firing showed tool marks and surface roughness that indicated incomplete final machining. Nakamura reviewed the inspection reports and made a decision that reflected both the pressure his team was operating under and the fundamental incompatibility between Japanese manufacturing practice and American design philosophy. He approved the components for assembly, reasoning that field testing would reveal whether the tolerances were adequate. If problems emerged, they could refine the manufacturing process in subsequent production runs. It was pragmatic thinking shaped by wartime urgency. It was also the moment when the project's failure became inevitable. The first complete prototype, designated HO 103 No. 1, was assembled in late September 1942. It looked magnificent, a nearly perfect visual copy of the Browning M2, finished in the dark blued steel that characterized Japanese military weapons. Iwakuro examined it with satisfaction, noting how the feed mechanism operated smoothly when cycled by hand, how the barrel change system functioned exactly as designed, how every control and adjustment matched the American original. On paper, in photographs, even in the hands of an experienced armourer unfamiliar with the Browning's internal specifications, the HO 103 was indistinguishable from its inspiration. The first firing test was scheduled for October 5, 1942, at Kokura's main proof range. The weapon was mounted on a fixed test stand, loaded with a 50-round belt of ammunition produced specifically for the test, using carefully selected cartridges inspected for dimensional consistency. Iwakuro, Nakamura, and a dozen engineers and technicians gathered in the observation bunker, their expectations balanced between hope and apprehension. At precisely 900 hours, the range officer gave the command to fire. The Ho-103 fired 11 rounds before jamming. The immediate problem was obvious, even from the observation bunker. The belt had failed to feed properly, causing a cartridge to become wedged at an angle in the feed tray. When technicians cleared the weapon and attempted to resume firing, it managed another 6 rounds before jamming again, this time with a failure to extract that left a spent casing wedged in the chamber. The third attempt produced 14 rounds before the bolt failed to lock fully into battery, preventing the firing pin from reaching the primer. Over the next 3 hours, with increasingly desperate adjustments and lubrication changes, the longest sustained burst achieved was 31 rounds. The average between stoppages was 17 rounds. The American Browning M2, by contrast, was routinely tested to 5,000 rounds without stoppage, and combat examples often fired tens of thousands of rounds before requiring anything more than barrel changes and basic cleaning. The gap between aspiration and achievement could be measured in jammed cartridge cases and frustrated engineers trying to understand why a weapon that looked perfect functioned so poorly. The investigation that followed the failed firing test consumed the next 6 weeks. Nakamura's team disassembled the prototype completely, examining each component under magnification, measuring critical dimensions with precision instruments, and comparing every surface to the captured American weapon. What they discovered was a catalogue of small deviations that accumulated into systemic failure. The bolt's locking lugs, which engaged matching recesses in the barrel extension during the brief moment when barrel and bolt travelled together in recoil, showed uneven contact patterns. Under firing stress, the lugs were making contact on only 60% of their bearing surface, concentrating forces in ways that caused premature wear and inconsistent unlocking timing. The extractor claw, which needed to maintain precise tension against the cartridge rim throughout the extraction cycle, was slightly too weak due to heat treatment that hadn't achieved the specified hardness. It would grip adequately for the first few rounds, then lose tension as it warmed up, leading to extraction failures. The feed mechanism revealed the most problematic issues. The Browning's feed system used a sliding block that moved laterally to position cartridges from the belt into alignment with the chamber. This component required surfaces machined flat to within 0.02 of an inch and polished to a mirror finish to reduce friction. The Japanese manufactured version showed surface waviness 3 times the specified tolerance and a finish that, while adequate for most applications, created friction that disrupted timing. As the weapon heated during sustained fire, thermal expansion magnified these issues, causing the feed mechanism to bind intermittently. But the most fundamental problem lay in the barrel itself. Without chrome plating, the Japanese barrel eroded rapidly from the hot combustion gases and copper fouling left by bullet jackets. After only 200 rounds of testing, bore measurements showed significant enlargement near the chamber end, where pressures and temperatures were highest. This erosion degraded accuracy and, more critically, altered the pressure curve that drove the recoil operation. As the barrel wore, the weapon's timing shifted, causing the bolt to attempt unlocking while chamber pressures were still dangerously high. Iwakuro reviewed the technical reports in his office overlooking the arsenal's main courtyard, where workers moved between buildings in the grey December light. The documents told a story he had feared but hoped to avoid. The Ho-103 wasn't failing because of any single flaw that could be corrected through refined machining or adjusted tolerances. It was failing because the entire weapon was a marginal design, operating at the edge of reliability, where any variation in ammunition, temperature, or component wear would push it into malfunction. The American Browning worked because every component was manufactured with precision that created reliability margins. The Japanese copy lacked those margins. It was like building a bridge designed with a safety factor of 5, using materials and construction methods that reduced the safety factor to 1.2. The bridge might stand under ideal conditions, but any unexpected stress would bring it down. The project team faced a decision that would define the weapon's ultimate fate. They could redesign components, investing months of additional development time to create indigenous solutions to the manufacturing challenges. This would mean effectively abandoning the goal of producing a direct copy and instead developing a new weapon inspired by the Browning's operating principles. Or they could push forward with incremental improvements, hoping that refined manufacturing techniques and component modifications would gradually improve reliability to acceptable levels. Iwakuro chose the second path, driven by pressure from the Navy's Bureau of Aeronautics, which was receiving increasingly urgent requests from fleet commanders for better aircraft armament. By early 1943, American fighters were appearing with heavier armor protection that rendered Japanese 7.7mm machine guns nearly useless. The 20mm cannons remained effective, but suffered from ammunition shortages as production struggled to meet demand across all services. The Ho-103, if it could be made to work, offered a middle ground that required less scarce ammunition than cannons, while providing far more hitting power than rifle-caliber weapons. Through the winter of 1942 and into the spring of 1943, Kokura Arsenal became a laboratory of incremental failure. Each prototype incorporated modifications intended to address specific problems identified in previous testing. The second prototype used a redesigned extractor with modified spring tension. It achieved 41 rounds before jamming. The third prototype featured a feed mechanism with hand-polished bearing surfaces. It reached 53 rounds. The fourth prototype incorporated a barrel made from a new steel alloy that promised better erosion resistance. It fired 37 rounds before a case head separation destroyed the bolt face. The engineers began to recognize a pattern that Nakamura described in his notes as whack-a-mole syndrome. Fixing one problem revealed or created another. Strengthening the extractor increased the force required for extraction, which altered timing and caused failures to eject. Reducing feed mechanism friction changed the belt tension requirements, leading to rounds being pulled from the belt at incorrect angles. Hardening components to resist wear made them brittle, leading to stress fractures that appeared after relatively few rounds. By mid-1943, the project had consumed over 18 months and significant resources, with little to show beyond a collection of failed prototypes and increasingly pessimistic technical reports. Yet, the pressure to succeed only intensified as Japan's strategic situation deteriorated. The Battle of Guadalcanal had ended in defeat, costing aircraft and pilots that could not be replaced. American submarine warfare was strangling resource imports, making every ton of steel and every gallon of chrome plating solution precious beyond measure. The war was becoming a race between Japan's declining industrial capacity and the growing effectiveness of weapons systems that Japan could observe but not replicate. In July 1943, Iwakuro received a directive that reflected desperation disguised as optimism. The Navy would accept the Ho-103 for limited production, even if reliability remained below American standards. Combat testing would provide data for further refinement, and any weapon was better than the inadequate armament currently equipping Japanese aircraft. Iwakuro understood what this order really meant. The Navy had given up on achieving true reliability and was settling for a weapon that might work well enough to make some difference in combat. The production version of the Ho-103 incorporated every marginal improvement the team had achieved. The barrel used the best available steel alloy with nitriding treatment that provided some erosion resistance. The bolt and locking components were manufactured from carefully selected billets and heat-treated using the most precise protocols Kokura's furnaces could maintain. The feed mechanism was hand-assembled by the Arsenal's most skilled craftsmen, who adjusted and fitted components to minimize friction while maintaining proper engagement. Each weapon took approximately 40 hours to manufacture, compared to roughly 12 hours for an American-produced Browning M2. This alone made the Ho-103 impractical for mass production, but the Navy's directive specified only 100 initial units for combat evaluation. At that production rate, Kokura could maintain quality control that would be impossible in larger runs. The weapons that emerged from this limited production effort represented the best that Japanese industry could achieve under wartime conditions. They were beautifully finished, carefully assembled, and thoroughly tested before delivery. They were also fundamentally unreliable. Acceptance testing at Kokura's proof range established an average of 212 rounds between stoppages, with individual weapons ranging from 147 rounds to 306 rounds. The Navy's minimum specification, hastily written to accommodate reality, called for 150 rounds between stoppages. By this deliberately lowered standard, most of the weapons barely qualified. The first combat deployment of the Ho-103 occurred in November 1943, when 12 weapons were installed in prototype fighters at Rabaul. The aircraft, Kawasaki Ki-61 Hien fighters modified, with two Ho-103 guns replacing their wing-mounted 20mm cannons, represented the Navy's hope that Japanese fighters could match the firepower of American aircraft. The pilots who flew these aircraft, veterans with hundreds of combat hours, approached the new weapons with skepticism, born of experience with previous wonder weapons that had promised much and delivered little. Flight Lieutenant Sakai Saburo, who had survived Guadalcanal and possessed one of the finest combat records in the Navy, test-fired his Ho-103 equipped Hien during a training flight on November 19, 1943. His after-action report, preserved in naval archives, provided the first combat pilot perspective on the weapon's performance. "The guns fire smoothly for the first few seconds," he wrote. "The recoil is less than the 20mm cannon, allowing better target tracking. But after approximately 30 to 40 rounds, the left gun jammed. I cleared it using the charging handle, resumed firing, and both guns functioned for perhaps 20 more rounds before jamming again simultaneously. This pattern repeated throughout the engagement. I estimate I fired less than half the loaded ammunition before the weapons became completely unreliable." Other pilots reported similar experiences. The guns would function adequately during the first engagement, giving pilots hope that the weapon might prove useful. But as barrels heated and mechanisms wore through initial break-in, reliability degraded rapidly. By the third or fourth combat sortie, most weapons were jamming consistently, often within the first few rounds of a burst. Armourers at Rabaul spent hours between missions disassembling, cleaning, and adjusting the weapons, but improvements were temporary. The fundamental design issues that Nakamura's team had documented months earlier were manifesting exactly as predicted. The combat reports flowing back to Kokura Arsenal throughout December 1943 painted a picture that Iwakuro found deeply troubling. The Ho-103 wasn't just less reliable than the Browning M2, it was less reliable than the weapons it was meant to replace. Pilots preferred the 7.7mm machine guns, which at least functioned consistently, even if their hitting power was inadequate. The 20mm cannons, despite their slow rate of fire and heavy ammunition, at least worked when the trigger was pressed. The Ho-103 combined inadequate reliability with complexity that made field maintenance a nightmare. American armourers could swap a Browning M2's barrel in under 2 minutes using a simple carrying handle and locking mechanism. Japanese armourers needed 15 minutes and specialised tools to change a Ho-103 barrel, assuming replacement barrels were available, which they increasingly weren't due to production bottlenecks at Kokura. The feed mechanism required adjustment after every few hundred rounds, a procedure that required precision gauges and experience that frontline maintenance personnel lacked. By January 1944, the Navy quietly suspended further production of the Ho-103. The official reason given was refinement of manufacturing processes. But everyone involved understood the truth. The project had failed. The 100 weapons manufactured were gradually withdrawn from service as they broke down beyond field repair. A few were retained at test facilities for continued development work that never produced meaningful improvements. Most were simply scrapped, their steel recycled for other weapons that actually worked. The post-mortem analysis, conducted by the Navy's Technical Bureau in early 1944-44, identified the core problem with brutal clarity. Japan had attempted to copy a weapon that was inseparable from the industrial system that created it. The Browning M2 existed because American industry could produce components to tight tolerances, because American metallurgy provided consistent material properties, because American ammunition production maintained specifications that Japanese factories couldn't match, and because American logistics could supply replacement parts and skilled maintenance personnel wherever the weapons deployed. Removing the weapon from this ecosystem and attempting to transplant it into Japanese service was like cutting a flower and expecting it to continue growing. The flower might look beautiful for a brief time, but without roots in proper soil, it would inevitably wither. The Ho 103 looked like a Browning M2. In every meaningful sense, it was not. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The comparison between American and Japanese manufacturing philosophies became impossible to ignore as the war progressed, through 1944. Intelligence reports reaching Tokyo detailed American weapons production at scales that seemed almost fantastical. The Browning M2 alone was being manufactured at rates exceeding 2,000 units per month across multiple facilities. These weren't handcrafted weapons assembled by master gunsmiths. They were mass-produced items that rolled off assembly lines where workers, many of them women with no previous manufacturing experience, performed repetitive tasks using specialized fixtures and gauges. The Buffalo Arms plant in New York employed over 5,000 workers, producing nothing but M2 machine guns and spare parts. The facility used assembly line techniques adapted from automobile manufacturing, with each major component moving through sequential workstations where specific operations were performed. A receiver started as a rough forging and moved through 23 separate machining operations before final inspection. At each station, workers used fixtures that held the part in precise alignment while they operated a single machine tool to perform one specific operation. The worker didn't need to understand the weapon's overall function or make judgment calls about tolerances. They simply followed procedures, using go, no-go gauges to verify that the operation met specifications before passing the part to the next station. This approach achieved both speed and consistency. A worker could become proficient at their specific operation within days, and because they performed the same task repeatedly, they became extremely efficient at detecting variations that might indicate tooling problems or material defects. The system was designed to prevent errors rather than catch them after the fact. If a part didn't fit the fixture properly, or if the go, no-go gauge indicated the operation had produced an out-of-specification dimension, the part was rejected before it could contaminate the production flow. Japanese weapons production operated on entirely different principles, rooted in craft traditions that emphasized skilled labor and individual judgment. A Japanese machinist working on gun components was expected to understand the weapon's function, read technical drawings, select appropriate tools and cutting parameters, and verify their own work using precision measuring instruments. This approach produced excellent results when materials were consistent, tools were sharp, and the machinist had adequate time to work carefully. Under wartime pressure, with material quality degrading, tool steel increasingly scarce, and production quotas doubling or tripling, the system broke down. The contrast manifested in every aspect of weapons production. American factories used carbide cutting tools that could machine hundreds of parts before requiring replacement. Japanese factories used high-speed steel tools that dulled quickly and required frequent sharpening, which consumed time and gradually reduced tool dimensions, affecting the accuracy of machined parts. American factories had dedicated inspection departments with specialized equipment, optical comparators that could measure complex contours, coordinate measuring machines that could verify multiple dimensions simultaneously, and metallurgical laboratories that could analyze material properties. Japanese arsenals had micrometers and calipers, operated by inspectors who were often reassigned machinists rather than trained quality specialists. The ammunition production comparison was equally stark. American .50 caliber ammunition came from factories like the Lake City Army Ammunition Plant in Missouri, which produced over 2 billion rounds during the war years. The cartridge cases were drawn from brass sheet in massive presses that shaped them with tolerances measured in thousandths of an inch. Each case was annealed to precise specifications to ensure consistent strength and elasticity. The powder charges were measured using automated equipment that varied less than 1/10 of a grain from round to round. The primers used chemicals mixed in batch reactors with sophisticated temperature control, ensuring consistent ignition sensitivity. Japanese .50 caliber ammunition production, limited to a few thousand rounds per month, relied on manual processes that introduced variation at every stage. Cases were drawn on smaller presses that required more operations to achieve final dimensions. Annealing was done in batch furnaces, where temperature control was approximate rather than precise. Powder charges were measured using balance scales, operated by workers whose fatigue and haste introduced variation. The result was ammunition, where chamber pressures could vary by 15% or more from round to round, where overall cartridge length variations affected feeding reliability, and where primer sensitivity ranged from too hard, causing misfires, to too sensitive, risking accidental detonation. The Ho-103's unreliability wasn't purely a function of the gun itself, it was equally a function of the ammunition feeding it. The Browning M2 could tolerate modest variations in ammunition quality because its design incorporated reliability margins. The Ho-103, already operating at marginal tolerances, couldn't accommodate even slight variations without malfunctioning. A cartridge case slightly out of specification would chamber properly in a Browning but jam in the Ho-103's tighter chamber dimensions. A powder charge on the high end of acceptable variation would cycle a Browning normally, but cause the Ho-103 to unlock prematurely, leading to case head separations. By mid-1944, Japanese weapons development had effectively abandoned attempts to copy American designs in favor of indigenous weapons optimized for Japanese manufacturing capabilities. The Navy's 20mm Type 99 cannon, despite its limitations, at least worked reliably because it was designed from the start to accommodate Japanese production methods and materials. The Army's 30mm Ho-155 cannon, developed as a bomber armament, used a simple blowback action that required less precision manufacturing than the Browning's recoil operation. These weapons weren't as sophisticated as their American counterparts. They fired more slowly, carried less ammunition, and required more maintenance, but they functioned, which made them infinitely more valuable than a theoretically superior weapon that jammed after 47 rounds. The lesson was expensive but clear. In industrial warfare, a reliable weapon that can be mass-produced is worth more than a sophisticated weapon that can't. The psychological impact of the Ho-103's failure extended beyond the immediate military implications. Japanese engineers and technical personnel had grown up in an educational system that emphasized mastery of foreign technology as a path to national strength. The Meiji Restoration's success had been built on importing and adapting Western industrial methods. Early 20th century, Japan had successfully copied and improved upon foreign designs in shipbuilding, steel production, and various manufacturing sectors. The inability to replicate something as apparently straightforward as a machine gun challenged fundamental assumptions about Japanese technical capabilities. If Japan couldn't copy a weapon that intelligence had documented thoroughly, that captured examples had revealed completely, then what did that say about Japan's ability to compete industrially with the United States? The answer was uncomfortable. Japan could compete in quality when time and resources were abundant, but it couldn't compete in quantity. And modern warfare was increasingly about quantity. The strategic implications rippled through Japanese planning during the final years of the war. Resources that might have been invested in copying advanced American weapons were redirected toward simpler indigenous designs or toward maximizing production of existing weapons. The emphasis shifted from achieving technical parity to achieving adequate numbers. Better to have 10,000 reliable but obsolescent weapons than 1,000 sophisticated weapons that didn't work. This shift represented a form of industrial surrender, an acknowledgement that Japan had lost the manufacturing war before the military war had ended. American industry wasn't just outproducing Japanese industry by factors of 3 or 5. It was operating on qualitatively different principles that allowed it to maintain quality while achieving quantity. The assembly line techniques, the specialized tooling, the statistical quality control, the logistics systems that supplied parts and maintenance personnel anywhere in the world. These were components of an industrial ecosystem that Japan couldn't replicate even if it had detailed blueprints for every piece. The Browning M2 continued its service throughout the war and beyond, eventually becoming the longest-serving military weapon in American history. Still in frontline use over a century after its initial design, its reliability became legendary. Stories circulated of weapons firing hundreds of thousands of rounds with nothing more than barrel changes and basic cleaning. Navy vessels mounted multiple M2S that fired continuously during kamikaze attacks, the guns running red-hot but never stopping. The weapon had transcended its role as a machine gun to become a symbol of American industrial power. The Ho-103, by contrast, disappeared from history. Few records survived, documenting its brief and unsuccessful service life. Post-war accounts of Japanese weapons development mentioned it only in passing, if at all. The engineers who worked on the project rarely spoke of it, the failure too painful to revisit. Iwakuro himself, interrogated by American technical intelligence officers after Japan's surrender, described the Ho-103 as an educational experience in the limits of industrial copying. When American investigators examined Kokura Arsenal after the war, they found several abandoned Ho-103 weapons in storage, covered in rust and cosmoline. One was selected for evaluation at Aberdeen Proving Ground, where American ordnance specialists test-fired it alongside a genuine Browning M2 for comparison. The test report, preserved in Army archives, noted that the Japanese weapon exhibits external similarity to the M2, but demonstrates fundamental differences in manufacturing quality and reliability. The weapon jammed repeatedly during testing, achieving an average of less than 100 rounds between stoppages. By contrast, the M2 fired 5,000 rounds without malfunction. The Japanese copy lacks the precision manufacturing and material quality that characterize the American weapon. The technical analysis that accompanied the Aberdeen report provided detailed measurements, comparing the Ho-103 to the Browning M2. Every critical dimension showed variation. The bolt face runout, which measured how perpendicular the bolt face was to the bore axis, exceeded specification by a factor of 3. The barrel chamber showed tool marks and surface roughness that American gunsmiths would have rejected as unacceptable. The feed mechanism's sliding surfaces exhibited wear patterns after only a few hundred rounds that indicated inadequate hardness and poor surface finish. But the most revealing finding came from metallurgical analysis of the steel used in both weapons. The American barrel steel showed a uniform microstructure with consistent hardness throughout, indicating precise control of alloying elements and heat treatment. The Japanese barrel steel showed significant variation in microstructure, with areas of inadequate hardness adjacent to areas that were too brittle. This inconsistency meant that different parts of the barrel wore at different rates, creating dimensional changes that disrupted the weapon's timing and pressure curves. The chemical analysis told an even more fundamental story. The American steel contained precise amounts of chromium, molybdenum, and vanadium, alloying elements that provided specific properties: corrosion resistance, high temperature strength, and wear resistance. The Japanese steel attempted to substitute more available elements, using manganese and silicon in place of the scarcer chromium and molybdenum. The substitution created steel that looked similar on paper, but performed differently under the extreme conditions of sustained firing. This pattern of substitution and approximation extended throughout the weapon. Where American designs specified brass for feed mechanism components, providing low friction and corrosion resistance, Japanese designers used phosphor bronze or even mild steel with surface treatments. Where American bolts used carefully controlled case hardening to create a tough core with a hard surface, Japanese bolts used through hardening that made them strong but brittle. Each substitution seemed reasonable, but collectively they transformed the weapon into something that merely resembled its inspiration rather than replicating it. The human cost of this technical failure manifested in ways that statistics couldn't fully capture. Japanese pilots who flew combat missions with unreliable armament faced psychological burdens beyond the obvious danger of inadequate firepower. They understood that their opponents, American pilots flying Hellcats and Corsairs, carried 8 or more Browning M2S that would function flawlessly throughout the engagement. They knew that when they pressed their firing buttons, their weapons might work or might not, making every combat encounter a gamble that had nothing to do with their skill or courage. Flight Lieutenant Sakai, who survived the war, despite being severely wounded multiple times, later wrote about the impact of unreliable weapons on pilot morale. "We could accept fighting an enemy who had more aircraft, better armor, or superior numbers. These were challenges that skill and determination might overcome. But fighting with weapons that betrayed us in combat, that jammed at the moment when our lives depended on them working, this was a form of betrayal that broke something inside. We began to doubt not just our equipment but the entire system that provided it. This erosion of confidence in Japanese industry's ability to provide adequate weapons affected not just frontline combat units, but the entire military establishment. Officers who had spent careers believing in Japanese technical superiority had to confront evidence that Japan was falling behind in fundamental ways. The inability to replicate a 30-year-old American weapon design suggested that the gap wasn't merely in production capacity, but in underlying industrial capabilities that made modern warfare possible. The contrast with American confidence was striking. American pilots in 1944 flew aircraft that were not just numerous but genuinely superior in most respects to their Japanese counterparts. They carried weapons they trusted completely, supplied by an industrial system that seemed capable of producing anything in any quantity. Their maintenance personnel had spare parts in abundance, technical manuals that were clear and comprehensive, and support systems that extended from the front lines back to factories in the United States. This material superiority translated into psychological advantage that was perhaps as important as the technical edge itself. By 1945, as Japan's situation became desperate, the contrast between American abundance and Japanese scarcity reached almost surreal proportions. American aircraft carriers operating off the Japanese coast carried more ammunition for their aircraft's Browning M2S than the entire Japanese military had in reserve for all weapons types. American bomber formations over Japanese cities faced anti-aircraft fire that was increasingly ineffective, not because Japanese gunners lacked skill, but because they lacked ammunition, spare parts, and working equipment. The economic data, analyzed after the war, revealed the scale of industrial disparity that the Ho-103 project had tried to overcome through copying. In 1944, the United States produced approximately 96,000 combat aircraft. Japan produced approximately 28,000. But raw numbers only told part of the story. American aircraft were increasingly sophisticated, incorporating technologies like radar, advanced fire control systems, and complex hydraulic systems that Japanese aircraft couldn't match. They were also more reliable, requiring less maintenance and suffering fewer mechanical failures. The machine gun comparison mirrored this broader disparity. American factories produced over 200,000 Browning M2S during the war years, along with millions of other machine guns of various calibers. These weapons equipped not just aircraft but ground vehicles, ships, and fixed defensive positions. The logistics system that supported this arsenal included dedicated ammunition production, spare parts manufacturing, and trained armorers who could maintain the weapons in field conditions. Japan produced fewer than 15,000 heavy machine guns of all types during the entire war, and many of these were plagued by the same reliability issues that had doomed the Ho-102. The philosophical difference between American and Japanese approaches to weapons development became a subject of study for post-war military analysts. American design philosophy emphasized reliability through over-engineering, accepting additional weight and complexity in exchange for weapons that functioned under adverse conditions. The Browning M2 weighed over 80 pounds without its mount, far heavier than theoretically necessary for its function, but that extra mass came from robust components that could withstand stress, heat, and rough handling without failure. Japanese design philosophy, constrained by material shortages and transportation limitations, emphasized lightness and efficiency. Japanese weapons were often elegant in their simplicity, using fewer components and less material to achieve their function. But this efficiency left no margin for error, no redundancy to compensate for manufacturing variations or material defects. When conditions were ideal, Japanese weapons performed admirably. Under the degraded conditions of late war production, they became unreliable to the point of uselessness. The Ho-103 represented the collision of these philosophies. Japanese engineers had tried to copy an American weapon that embodied American design values: overbuilt, tolerant of manufacturing variation, reliable under abuse. They had attempted to manufacture it using Japanese methods and materials that couldn't support those design values. The result was inevitable. A weapon that looked right but performed wrong, that promised much but delivered little, that consumed scarce resources while contributing nothing to Japan's military capability. In the decades after the war, as Japan rebuilt its industrial base and became a manufacturing powerhouse, the lessons of the Ho-103 project were remembered, if not always explicitly discussed. Japanese industry embraced quality control methods pioneered in the United States, particularly the statistical process control techniques that had enabled American wartime production miracles. Companies like Toyota developed manufacturing systems that emphasized consistency, continuous improvement, and elimination of variation, precisely the capabilities that had been lacking during the desperate days of Ato's wartime production. The irony was profound. Japan had failed to copy the Browning M2 during the war, but succeeded in copying and improving upon the industrial methods that had made the Browning M2 possible. The lesson learned was that technology transfer isn't just about blueprints and specifications. It's about the entire ecosystem of knowledge, capabilities, and systems that enable technology to function. Trying to copy a finished product without understanding and replicating the system that created it is like trying to transplant a tree by cutting off its branches while leaving the roots behind. Modern Japanese defense industry, constrained by constitutional limitations and political considerations, still faces challenges in developing certain weapons systems. But when Japan does develop military technology, it typically works reliably because the underlying industrial base can now support sophisticated manufacturing. The F-2 fighter, developed jointly with the United States, incorporates components that require precision manufacturing comparable to or exceeding what was needed for the Browning M2. Japanese factories produce these components successfully because they have the machine tools, quality control systems, skilled workforce, and material science knowledge that Kokura Arsenal lacked in 1943. The story of the Ho-103 serves as a case study in the relationship between industrial capability and military power. Japan's defeat in World War II was not primarily due to lack of courage or tactical skill among its military personnel. It was due to industrial capacity insufficient to sustain modern warfare against an opponent whose industrial capacity seemed almost unlimited. Every failed weapons project, every aircraft that couldn't fly due to lack of spare parts, every machine gun that jammed in combat, represented not individual failures but symptoms of this fundamental disparity. The Browning M2, still in service with armed forces around the world, has fired billions of rounds in combat from World War II through conflicts in the 21st century. Its reliability has become legendary, its design so fundamentally sound that attempts to replace it with more modern weapons have repeatedly failed to produce anything demonstrably better. The weapon has outlasted the empire that tried to copy it, outlasted the Cold War, outlasted the Soviet Union, and continues functioning in environments from Arctic tundra to desert heat. The Ho-103 fired its last rounds in combat sometime in early 1945, most likely during desperate defensive actions as American forces closed in on the Japanese home islands. No records document its retirement from service because there was no formal retirement. The weapons simply broke down, one by one, and were either abandoned or scrapped. No examples survived into the post-war period in working condition. The few that exist in collections are non-functional, remnants, historical curiosities that illustrate a failed ambition. In the archives of the Japan Self-Defense Forces, a single photograph preserves the image of Colonel Iwakuro standing beside a completed Ho-103 in the Kokura Arsenal workshop. The date stamp indicates November 1943, shortly before the weapons entered their disastrous combat evaluation. Iwakuro's expression is carefully neutral, showing none of the pride or satisfaction typical of such photographs. Perhaps he already knew, or suspected, how the story would end. Years later, during an interview conducted for a military history project in the 1970s, Iwakuro was asked about the Ho-103 project. His response, recorded in the interview transcript, revealed both the technical understanding and the resignation of someone who had lived through the experience. We believed that if we could see a thing, measure it, and document it thoroughly, we could reproduce it. We learned that some things cannot be copied because they are inseparable from the system that created them. The Browning machine gun was not just a mechanical device, it was the product of an entire industrial civilization. We tried to copy the device while lacking the civilization. That was our fundamental error. The interviewer pressed Iwakuro on whether, with more time and resources, the project might have succeeded. His answer was unequivocal. Time and resources would not have solved the essential problem. We would have needed to transform our entire industrial base, our manufacturing methods, our supply chains, our quality control systems. We would have needed to become, in effect, America, and if we could have done that, we would not have needed to copy their machine gun, because we would have had the capability to design our own superior weapon. The Ho-103 failed because it asked Japanese industry to be something it was not and could not become during wartime. That is not a criticism. It is simply reality. This reality extended far beyond a single weapon project. The same patterns that doomed the Ho-103 affected dozens of other Japanese attempts to copy or match American and British technology during the war years. Every project encountered the same fundamental problems: inadequate precision manufacturing, inconsistent materials, insufficient quality control, and logistics systems that couldn't deliver parts and support to where they were needed. Some projects failed completely, like the Ho-103. Others produced marginally functional weapons that served primarily to illustrate how far Japan had fallen behind. The strategic implications were understood at the highest levels of Japanese government by 1945, though this understanding came too late to affect the war's outcome. Internal documents from the final cabinet meetings before surrender show clear recognition that Japan could not match Allied industrial capacity, and that continuing the war would simply accelerate Japan's complete destruction. The Ho-103 and projects like it had demonstrated that Japan couldn't bridge the technology gap through copying, couldn't overcome material shortages through ingenuity, and couldn't substitute determination for industrial capability. In the end, the story of Japan's attempt to copy the Browning 50 caliber machine gun is a story about limits. The limits of what copying can achieve without understanding, the limits of what manufacturing can produce without adequate tools and materials, the limits of what courage and skill can overcome when the fundamental balance of industrial power is overwhelmingly against you. These limits were written in jammed cartridge cases, broken extractors, and worn barrels that eroded after a few hundred rounds. They were measured in pilots who faced combat with weapons they couldn't trust, and engineers who worked desperately to solve problems that had no solution within the constraints they faced. The Browning M2 and the Ho-103 sit at opposite ends of a spectrum that defines modern warfare. One represents what industrial civilization can achieve when resources, knowledge, and capability align. The other represents what happens when ambition exceeds capability, when necessity demands what reality cannot provide, when the gap between aspiration and achievement becomes unbridgeable. The 47 rounds fired before jamming weren't just a technical failure. They were a mathematical proof of Japan's strategic position, expressed in the language of metallurgy, manufacturing tolerances, and mechanical reliability. Today, military museums occasionally display examples of both weapons side by side. Visitors can see the external similarity, can note the careful attention to detail in the Japanese copy, can appreciate the engineering ambition that drove the project. What they cannot see, cannot feel in their hands or hear in the silence of museum halls, is what those weapons meant to the men who tried to use them. The frustration of pulling a trigger and hearing the mechanical click of a jam instead of the satisfying roar of sustained fire. The terror of facing an enemy whose guns worked while yours did not. The resignation that comes from understanding that you're fighting a war your nation has already lost in factory floors and assembly lines thousands of miles from any battlefield. The lesson, like the Browning M2 itself, has endured. In an age of precision manufacturing, global supply chains, and instant information access, the Ho-103 reminds us that knowing how something works and being able to make it work are profoundly different things. Technology exists within systems, and copying technology without replicating those systems produces, at best, expensive approximations and, at worst, dangerous illusions of capability. The gap between the American original and the Japanese copy was measured in thousandths of an inch, in percentage points of alloy composition, in degrees of heat treatment temperature. But it represented something much larger, the difference between an industrial system operating at the peak of its capability and one struggling at the limits of its capacity. The 47 rounds fired before jamming became, in their way, as historically significant as the millions of rounds fired successfully by Browning M2s throughout the war. They demonstrated that World War II was decided not in the moments of individual combat between skilled pilots or courageous soldiers, but in the accumulated capacity of industrial systems to produce reliable weapons in sufficient quantity. Japan lost the war in places like Kokura Arsenal, where engineers stared at failed prototypes and understood that their nation lacked the industrial foundation to compete. America won it in places like Buffalo Arms, where workers who had never seen combat produced weapons that never failed those who carried them into battle. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.